This lecture is, it tries to strike a difficult balance. As you all know, relaxation theory is horrendous. And so when I had these discussions with Kirill about what he wanted to see, we agreed that I should put the mathematics level, pitch it generally at about the first year PhD student. So that's the level of the discussions that you would have here. Also, we are pretty boxed in for time, so I would suggest that we leave all the questions till the end of the lecture. Otherwise, we are quite certain to run out of time. Okay, so spin relaxation theory. All of you will encounter this at some point as magnetic resonance specialists, and all of you will notice that it is next to impossible to do it by hand for anything bigger than a single spin, because the mathematics involved is an arcane combination of stochastic differential equations, really seriously difficult spin dynamics, group theory, rotation theory, and a lot of the Lie groups and Lie algebras that are not really taught within the physics department. So it's a steep learning curve, but I've tried to reduce it to something that is both sufficiently sophisticated to illustrate the general picture, but also sufficiently simple to fit into a talk like that. Okay, so what is relaxation? It's a process where an ensemble of systems returns to equilibrium. And the keywords here are ensemble, so there's no such thing as relaxation in a conventional sense in a single quantum system. You need an ensemble of those systems. And second is equilibrium, which is again a notion from statistical thermodynamics, right? In order to have a thermal equilibrium, you need to have a concept of temperature, and therefore you need an ensemble. So relaxation, at least in the sense that is described in this lecture, is about an ensemble of systems coming back to thermal equilibrium. And all of you as magnetic resonance people have seen the experiments, or as undergraduate chemists even. If you flip the spins around, they will slowly recover. This is called inversion recovery. Or if you put the magnetization in the transverse plane and then repeatedly refocus it using a repeated spin echo pulse sequence, car per cell, for example, you will also see a decay. And this is called longitudinal relaxation because the magnetization is on the z-axis, and this is called transverse because it is in the transverse plane. Now, principally, relaxation is caused by noise. Every physical system would have some noise in it, and that noise would have a frequency spectrum. So if we take the noise and we Fourier transform its square, we will have something called power density. So at some frequencies, the noise is loud, and at other frequencies, it is quiet. And there will be frequencies that match the transition frequencies in our quantum systems. And so the noise will trigger spontaneous transitions, random transitions up and down. And so the system will spontaneously return to thermal equilibrium because transitions one way are slightly more probable than transitions the other way. There are many sources of such noise, Brownian motion, for example, or phonons, vibrations in solids, conformational mobility in flexible molecules, bumping into walls and into solvent and such like. So essentially, whenever that noise has a component at the frequency of our transition, you will see relaxation across that transition. Now, importantly, the mathematics of the process has to take into account the stochasticity of that noise. And this is where the problems begin, at least on the mathematical side. You see, noise doesn't play well with the differential equations that we have in quantum mechanics. Noise is often not differentiable and occasionally not even integrable. Imagine you have this Hamiltonian, which is the static Hamiltonian, and then there will be some noise in Schrödinger's equation. And you know how to solve this when h is time independent or it's smooth in time, but it is very difficult to solve it when h1 is, for example, Brownian noise. And then the solution will be a noise of a different kind. And here's an example, right? If you feed some noise into a dynamical system, for example, its integral will come out, and this often happens in quantitative finance, for example, you get a different type of noise out. And so the way to solve such stochastic differential equations is to express the solutions not in terms of an instance of the noise, because it will be different in every individual molecule, but in terms of the statistical properties of that noise, like mean and standard deviation and distribution law, various statistical functions like autocorrelation functions, because those are generally differentiable and well behaved. And you have all seen examples of such situations. If we look at a molecular dynamics simulation of liquid water, for example, the position of every water molecule is random, and at any given point, whether there's a water in it or not is also entirely random. But there are functions like, for example, the probability of seeing another oxygen a certain distance away from this oxygen, which are actually continuous and differentiable. This is the autocorrelation function of liquid water and liquid argon. And even though each individual instance of the dynamics is random, there are some statistical functions which are well behaved here. And there are other types of spectral power density, for example, so statistical properties of noises. Dima, in fact, just mentioned this. If you take music, these jumping bars in your music player are actually the spectral power density function of the noise. And you can see at some frequencies it is quiet, and at other frequencies it is loud. So noises vary significantly in their spectral power density functions. And if this particular frequency hits our transition frequency, we will have efficient relaxation in the system. What is very important is that in practice, most noises are stationary. That is, even though each individual instance of the noise might wibble and wobble, the statistical parameters, like for example these functions, do not depend on time. Like the distribution law of the noise is fixed. Such noises are called stationary, so their statistical parameters do not depend on time. Okay, so let us now take a look at Schrödinger's equation. So this is it, that's our Hamiltonian, that's the wave function, and this is the noise that we have in the system. Now, solving this is actually a couple of hours of seriously dense mathematics, and as per our discussions with Kirill, I decided to replace this with something that is just as sophisticated, but just a little bit simpler on the mathematics side. So instead of this being an operator, here and here, I decided to make this a scalar. So we will still have an oscillatory process, much like the original Schrödinger equation had been, but we will have a fixed frequency and a random noisy frequency. So the Hamiltonian is effectively one-dimensional. Let's think about what this corresponds to. If we take a spring and a load on a spring, if we stretch it and let go, it will wibble and wobble. And the coordinate will depend on time as a cosine of a certain frequency. And then momentum is the derivative of that times the mass. So we will have this. And we can put it together, the coordinate and momentum, into a complex exponential. And those of you who did physics would recognize the phase space, right? And then it's a complex exponential. So actually, physically, this simplification corresponds to just a weight on a spring. And this little noisy term means that somebody is sitting and rattling our spring, like throwing grains of sand into it. We have a frequency, but the frequency is noisy. Okay, we will assume that our noise has a zero mean. It is a centered noise. So the ensemble average, or equivalently a sufficiently long time average of it, is zero. And we can always do it because if it's not zero, we can subtract it out and put it into omega naught. So this is not even an approximation. And we will assume that the noise is stationary, like it would be in most liquids. Right? Every instance is different, but the statistics is exactly the same. And in real magnetic resonance experiment, this omega naught would be the Zeeman frequency, and this would be, for example, the chemical shielding anisotropy. Molecule tumbles, and the Hamiltonian is modulated. And every anisotropic term in it, like the dipolar coupling, for example, would also be modulated by just the random motion of the molecule in the liquid. Okay, let's look at this equation. We have a deterministic part here, this omega naught, and we have a stochastic part. And we actually know what the deterministic part does, right? It turns the system around. So, and we know that relaxation is multiplicative. So we expect, intuitively, at least it's highly educated intuition, but still, there to be an oscillation times some decay. So why don't we use this ansatz and put it into here and see if something simplifies. So I will take this f and I would substitute it there and simplify. And actually, this corresponds to the rotating frame transformations that you have in magnetic resonance, where the dominant dynamics is, by exactly this kind of substitution, is eliminated from the equation of motion, and we can then focus on just this decay. Okay, so when we put that into here and do the simplifications, we notice that omega 0 disappears from the equation, and we now just have omega 1. So we took out the known oscillation, and we now focus on the interesting part, which is how that oscillation is going to decay. Okay, so as I mentioned, this is stochastic, and there are no easy ways to solve this directly, and no ways to average things, because wave functions don't like averaging, right? Phases are random in quantum mechanics, and if you just average the wave function over the ensemble, you just get 0. So our only hope to solve this is to obtain a solution in terms of the statistical properties of this noise. And the particular statistical property that I will target is this autocorrelation function. And it's actually a glorified correlation coefficient. So this correlation coefficient you have all seen. It's just a measure of linear dependence. And we can simply take that and copy it into a continuous variable, and then we will have this autocorrelation function. And for even stochastic noises, this tends to be well behaved. So we will try and seek solutions for the stochastic differential equations in terms of these autocorrelations. Okay, so all problems with the noise would disappear if we manage to do that. Okay, so let's do the following. I will take these equations that we have, and I will integrate both sides, just because I can, for no particular reason so far. So this will be phi of t minus phi of 0, and this will just be the integral of that. And I will put phi of 0 over to the right-hand side. So we've got the equation, which is equivalent to the original equation. There are no approximations here. We've just integrated both sides for no particular reason, just because we can. What I will then do is I will take this phi and I will substitute it back here. Again, for no particular reason, just because I can. And then we have this expression in here. Now notice what we have here. We have something that begins to resemble that autocorrelation function that we wanted to obtain, except there's no ensemble average here yet. So why don't we ensemble average this equation and see what's going to happen? So when we ensemble average that, it'll just be the average of phi. We don't know what it is. However, remember the assumption that we made a few slides ago about the ensemble average of this. The ensemble average of this was 0. And the initial condition is the same in every member of the ensemble, so that goes out of the bracket. So this averages to 0. It disappears. And then ensemble averaging is a linear operation, so the ensemble average of the integral is just the integral of the average. And so we have a slightly simpler equation, which now comes a little bit closer to getting that autocorrelation function that we wanted to obtain. And in fact, if you go through the physics of the process, what we've just gone through is actually time-dependent perturbation theory. It's just not everybody in the audience had time-dependent perturbation theory in their courses, so I've just cast it as a sequence of legitimate mathematical transformations. And this is really as far as we can get without making any assumptions. So this equation is still formally identical to the original stochastic differential equations that we have, except for the averaging. But let us now proceed and start making approximations. So the first thing that we will do is we will assume that the noise is too weak to drive the system. That is, it contributes to the system, it relaxes the system, but it's not strong enough to really swing it around. So the principal frequency that we have is there, but the noise is much weaker than that. So we essentially say that the noise is not correlated with the dynamics of the system. It's too weak. And under that assumption, this joint average is split into the average separately over the noise and separately over the system. That's our assumption, that the dynamics of the noise is uncorrelated with the dynamics of the system. Okay, the next thing we will remember that we had assumed about this noise is that it had been stationary. Now, this really is now an autocorrelation function, and for a stationary noise, it's going to be exactly the same tomorrow as it has been yesterday. So it cannot depend on absolute t and t prime, but only on the difference between t and t prime, because this t can be tomorrow, right? And the statistics is the same tomorrow as it had been today. Okay, so it can only depend on the difference. And then in order to have a normalized function in here such that g of 0 is 1, we will take a coefficient out. So we will have something that is the root mean square amplitude of this, just the mean square really without the root, because we've got two of these, and some autocorrelation function that is now normalized. So this is the property of the noise itself, and it can only depend on t minus t prime. Okay, so let us now take this and put it back under our integral that we had. That's actually an illustration, right? If we have some stochastic dynamics with a little bit of determinism underneath it, it's being pulled out into deterministic form by an autocorrelation function. Okay, so take all of that and put it under the integral. So from 0 to t in t prime, that means t minus t prime is always positive, so the modulus disappears, and we now have a different form of that equation. What I will now do is I will do a variable substitution here. It's a bit of a technicality, but it's a straightforward mathematics that swaps t and t prime, and then you get this integral out of it. And so we have this autocorrelation function of the noise, and we've got the dynamics of the system. Now notice that the stochasticity is now gone. The original equation contained the noise itself, but this only contains the statistical parameters of the noise, which means we've just replaced a stochastic differential equation with an ordinary differential equation, integral differential, but hey, at least we know how to solve it. Okay, let's try and solve it. If we look at what we have here, we'll drop the brackets, so we'll just assume that that's already an ensemble average, and we will reverse the substitution, right? Remember, our phi was related to the original variable f by this exponential. So let's now put this back into here and simplify it a bit. So we now have df by dt, so the dynamics of our weight on a spring is actually composed of two parts. One looks like the differential equation that we would have had if we didn't have any noise at all, right? Just the omega naught, the principal frequency, and the f. So if we solve this alone, we would have the cosine and the sine, and it would be moving as if it didn't relax. But now an extra term appears, which is actually negative, right? If you look at these, that is and in its entirety a negative number, and then it dumps the functions that we have, and it has something to do with the noise. So let us now take a good look at this extra integral that we have here. So we will assume that the memory time of our noise is really short, and it's actually true in liquids. Typically, the molecule loses its memory of where it had been rotationally in a few nanoseconds. And the dynamics that you've seen in the spectra that you've seen so far is in the seconds, right? Milliseconds at most. So really, this autocorrelation function decays really rapidly, and it dumps this integral nearly instantaneously. And so we might as well replace this t with infinity, because we would be integrating over just a track of zeros. The second thing we will notice is, because this really decays so quickly, this t minus t prime is just as good as t. So we can make two assumptions. Firstly, that t prime is much smaller than t, because the memory time is so short, and so f of t minus t prime is just the same as f. And the second thing is we can extend the integration limit here to infinity. At this point, this becomes a Fourier transform of this autocorrelation function. And those of you who have done the relevant math would remember that this is actually the spectral power density. It's just those jumping bars of how loud your noise is at each specific frequency omega naught. Okay, so these are probably the least obvious and least easy to understand assumptions. They are called coarse graining of time. I'm pretty certain Redfield himself was kinda iffy about them, but they work, right? In non-viscous liquids, they really work. And you can see the validity condition here. The relaxation theory only works at any field, big or small, when noise is really fast, in practice much faster than the characteristic time of the system dynamics. And this is usually true in non-viscous liquids. Okay, so our final equation of motion is this. And let's now take a look at the various components of it. So this Fourier transform that we have of the autocorrelation function has a name. It's a spectral power density. It's how loud the noise is at our transition frequency. Remember what I told you about at the very beginning, right? The efficiency of relaxation depends on how loud the noise is at our transition frequencies, and that's basically how loud it is. So this SPD is noise power at each frequency. Then what we also have is this prefactor, right? This was the amplitude of the noise, right? This is the mean square amplitude. So the efficiency of the relaxation depends on the square of the noise volume, and then on the spectral distribution of that volume. So this overall decay rate and the overall frequency now have a physical interpretation. This part of the equation is just the original oscillator, and this is the damping of the oscillator. And the damping rate is quadratic with the volume of the noise and really depends on how that volume is distributed across frequencies. And of course, then the overall result is our decay oscillation. And so we did it, we solved the equation, and you can see even for the simplest systems, this is seriously tough. And noise, its effect is in a certain perturbative regime to make our ensemble of oscillators irreversibly go out of phase, and this is called relaxation. So remember, quadratic in the amplitude and depends on the distribution of frequencies within the noise. All right, so this was a weight on a spring. Where does noise enter our spin Hamiltonians? So this is the most general horrendous spin Hamiltonian for some horrible radical in some really complicated system. It would have the Zeeman terms, the internuclear couplings, the electron nuclear couplings, the interelectron couplings, and microwaves and radio frequency fields, and perhaps zero field splitting and what else you can have in such systems. So firstly, Zeeman interactions. At zero field, you don't have this problem, but at high field, we do. The shielding tensors are all mostly anisotropic. And that's a plot of how well a nucleus is shielded in, I think this is strychnine. And you can see some of them, particularly in the aromatic systems, are pretty anisotropic. When this molecule tumbles around in a non-viscous liquid, every time it turns relative to the magnetic field, you will have a different Zeeman Hamiltonian. Tumbling is random, so we get a noise in here. So you have the interaction between the external field and the electron spin operators, and external field and the nuclear spin operators, and these are trigonometric functions of the orientation. And this is how the relaxation happens. Remember the previous slide, the rate was quadratic with the amplitude, and so this chemical shift anisotropy, CSA relaxation, is quadratic in the magnetic field. And this actually means that bigger magnet isn't necessarily a better magnet. For certain things like fluorine-19 spectroscopy, the sweet spot is actually at 500 megahertz. If you buy yourself a gigatoy or a 1.2 gigahertz, you would notice your fluorine spectroscopy is actually getting harder rather than easier. But for protons, of course, higher field is better because proton CSAs tend to be a bit smaller, and you can play the CSA against other interactions. Strozzi effect, for example. If you Google it up, you will see that. Then internuclear and quadrupolar couplings, actually quadrupolar interactions weren't covered at this conference because they're so much stronger than everything else that is going on. But you will have functions of conformations. Your J couplings depend on the angles in the system. And because conformation is stochastic in many things, you will have some noise there. Quadrupolar interaction is anisotropic. It's a function of orientation. Dipolar interaction between the spins is anisotropic, likewise a function of orientation. All of that becomes noisy, And you can probably look at this equation and instantly tell why I decided to give you a ball on a spring as an example. Imagine if we had to crack through something like this in a tutorial lecture. The only thing that I would have done is confuse the hell out of everyone. So the actual relaxation theory is horrendously complicated. It takes years to get it. Okay, so electron-nuclear interactions like hyperfine couplings, they are really seriously anisotropic. For example, in this aromatic radical, it's a pyrene-cation radical, I think, one direction dominates. And they're really much stronger because they involve an electron, so multiplied by 600. That tends to dominate in paramagnetic species. Okay, let's take a look at spectral power densities as well. So at this J of omega. In a liquid, if you look at Brownian rotational diffusion on a sphere and calculate that autocorrelation function, turns out to be an exponential. And when you do a Fourier transform of the exponential, you get a Lorentzian shape and a little small imaginary component in here. And this is why you have these Lorentzian curves everywhere in magnetic resonance. That's because they are Fourier transform of a decaying exponential that comes out of these statistics. Now, in liquids, we are quite lucky in that all of this is straightforward. In solids, the situation is quite bad, because phonons have really complicated frequency spectra, and also they do behave quantum mechanically, so the population of every phonon mode can get depleted, for example, halfway through the relaxation process. And so phonon spectrum of most solids and spin-phonon coupling particularly are really hard to predict, and this is literally the 2020 kind of science. We just accepted a paper at Science Advances from a team who did DFT calculations on an enormous supercomputer across every vibrational mode they could find in a crystal to get these spin-phonon couplings. And even they, after heroic effort, are in order of magnitude out, which is like, it's the astronomical order of magnitude. That means you basically solved the problem. So this is tough. In liquids, it's more or less solved. In solids, this is an ongoing effort. Cross correlations. Now look at this tumbling molecule here. Notice that even though the thing would tumble randomly in any solution, the relative orientation of these tensors is actually non-stochastic. They tumble perfectly synchronously. This is called a cross correlation, and it leads to a bunch of sophisticated relaxation effects. One of them is called TROSY, where you can have occasionally the lines that are really narrow. And this can be exploited in magnetic resonance, where if you play your various anisotropies really well against one another, lines can become considerably narrower than they otherwise would have been. So that's an example of a carbon-fluorine TROSY effect. For example, if you pick the wrong component of a multiplet, at 800 megahertz, it's 120 hertz, basically useless. But if you pick your multiplet component right and pick the field right, you can have a line width less than 10 hertz, which for protein and mass spectroscopy is seriously awesome. This is fluorotyrosine in ubiquitin, by the way. Otherwise the lines would be really, really broad. The way the theory is done, essentially, so that's the summary, is your molecule tumbles, that generates the noise in the Hamiltonian. And when you go through this entire lecture, but for the actual Liouville van Neumann's equation rather than the ball on a spring, you get this integral. It's called Redfield's integral, with these autocorrelation functions between irreducible spherical components of the Hamiltonian. These are the irreducible spherical components. I don't want to tell you what irreducible spherical means. You will pick it up from the books along the way, and that's the H naught. So this is a seriously tough integral. For anything more than a 3-spin system, it only ever became possible to compute these things around about 2010. But the good news is all of this is handled automatically within, for example, spinach. You specify your interactions and isotropy correlation times, press enter, and the relaxation superoperator just pops out. In liquids, that series is pretty accurate. It's around 10% that we usually get if your parameters are good. So that's a solved problem. And so One piece of warning that I would give you is don't try to do relaxation theory by pencil and paper. You would lose a great amount of time and get stuck in all the nested commutators. If you insist on analytical treatment, use Mathematica, right? Malcolm and company in Spin Dynamica do have some analytical tools. We've got some Mathematica scripts enclosed with Spinach that do this analysis semi-automatically. It's really, I think Art Palmer at some point had spent an entire chapter of his book going through just a two-spin system with a dipolar coupling. It's really horrendous. And then there are plenty of errors in the published literature. Do not use published equations unless you've checked them against the numerics, because minuses are lost all over the place, particularly in cross-correlation terms. Yeah, it tends to be quite a mess, particularly for the older papers that were published before the computers were around. That's an example of relaxation syntax in Spinach. You specify your magnet field, your isotope, your CSA, for example, and just say relaxation equals Redfield, equilibrium equals DeBary. This is the famous paper of DeBary and Levitt on thermalization. Relaxation laboratory frame, so keep all the secular terms and the non-secular ones as well, correlation time, and press enter and it will just speed it out. And it supports every interaction there is in magnetic resonance, and all cross correlations are accounted for automatically. Our script in Mathematica, just say rate and so on. It spits out all the standard relaxation rates. You can be a bit more flexible in Spin Dynamica, but there I think it's only the extreme narrowing limit. So there are standard packages that do it, both in MATLAB and Mathematica. Now, decades of work have gone into this. Use it, right? So again, there's this health warning in that trying to rederive that thing is a very long story. Another health warning is that Redfield theory is a perturbative relaxation theory, right? We are making assumptions about the noise being fast. If the noise isn't fast relative to system dynamics, it's not going to work. So that's the Redfield theory, Bloch-Redfield-Banks test. That's stochastic Liouville equation, a much more sophisticated formalism that we have in Spinach, as well as this. And let's take a look. So correlation time of 5 nanoseconds when the noise is faster than the dynamics, perfect match. Correlation time 50 nanoseconds, typical protein, perfect match. All right, 500 nanoseconds, it really shouldn't work, but mysteriously it does, perfect match. 5 microseconds, nobody knows why Redfield still works, but it does. However, when you start really pushing it and going into seriously viscous things like, crystalline glycerol, then there is a mismatch, right? Redfield theory breaks down, SLE correctly gets sort of a powder pattern starts emerging. And finally, when you are pretty much in a solid, stochastic Liouville equation correctly gives you the solid powder, and the Redfield theory is completely broken. Okay, so essentially, Redfield theory is strictly valid only for correlation times below 100 nanoseconds, which means a very big protein. If your system is bigger or slower than a very big protein, don't use it. At that point, things become really complicated. So, summary of the talk. Spin relaxation is caused by noise in the Hamiltonian that hits transitions if the frequency matches this relaxation. It is quadratic in the noise amplitude, and it depends on the frequency distribution within the noise. Full quantum mechanical treatment is stupidly hard. Use the standard software, which thankfully exists and will do most things for you. I would plug for Spinach, which actually have a Zulf module in it already. It's a collaboration with both Dimas Crew and Thomas Theis, who I visited at some point, and we wrote that module with them. In the latest developer version, you've got slightly more sophisticated Zulf experiments as well. It will be released in a couple of weeks when the next MATLAB comes out. And that's basically the summary. So there's your fixed frequency oscillator, there's your noisy frequency oscillator. And if you average over a bunch of noisy frequency oscillators, you get a decaying frequency. And this is what relaxation theory really is all about. Liquids are fine. Solid state relaxation theory is not quantitative because there are too many unknowns in there. And now I'm happy to answer questions.
Thank you. It was a great talk. So now we have some question. John was asking, how does ensemble relaxation time related to single system correlation time, for example, single molecule?
You see, we are here in a dangerous regime. We are trying to apply thermodynamic notions to a single molecule. We can only do it in the sense of the ergodic theorem, right? That if we observe that molecule under some stochastic process for a really, really long time, then probably the average of that observation is going to be the same as the ensemble average. So that's the strict relationship, I think, that you are asking about. So the ergodic hypothesis, it's probably not a hypothesis, it's probably a fact, but there are certain systems in physics which are non-ergodic for various difficult reasons, like they couldn't snap out of a particular dynamic orbit and don't explore the phase space fully. So essentially, the infinite time limit of observing an individual molecule is the same as the observation of an ensemble, assuming the dynamics is ergodic.
Okay. I guess maybe if I can add on to that, so the general logic, especially in these, sort of single NV detected cases, and any other case where you have this spin noise measurement, is that your correlation time of that spin noise is essentially equal to the normal T2. Is that really just the consequence of this ergodic hypothesis, or is there any other way to have that make sense?
It's a difficult question. We are comparing the incomparable. I would be very careful about applying thermodynamic limit results to individual systems, because in an individual system, the very notion of relaxation, you have to be much more careful about the ground state. You have to be more careful about the mathematical properties of your relaxation superoperator. It has to obey certain Lie algebraic constraints. It has to be a semi-group, right? It has to be trace preserving, has to be positive, and so on. I really would say that what I have said strictly applies to ensembles, like a solution. And if you are looking at dynamics of individual molecules, it's a very different picture.
I guess John also had a connected question. What happened when everything is noise?
Nothing much, exactly the same. So you would have a system that's driven by the noise, but you see the characteristic time of system dynamics, they are still there, right? Even though your, for example, primary field is absent, the Zeeman interaction is still there. So even though the system only has noise, its characteristic time of response to that noise is still the property of the Hamiltonian. So long as the dynamics of the noise is much faster than the resulting relaxation process, everything I've talked about still applies. So your noise has to be much faster than the system and must have a much shorter memory time than the system. Otherwise, there are no constraints.
Thank you. So we have another question from Quentin. Redfield theory is valid only for tau c less than 100 nanosecond. Is it regardless of the field?
It's not that 100 nanoseconds is a rule of thumb for high field liquid state NMR. So the rigorous condition, in fact, foreseen by Redfield and worked out, I don't remember who worked it out, somebody after him a few years later, but essentially the slowest relaxation time in your system has to be much shorter than the fastest relaxation rate. Right? It's a subtle thing. So essentially, the true norm of relaxation superoperator has to be much smaller than 1 over tau c. So that's the rigorous applicability condition of Redfield theory. And actually, if you use Spinach, we do have posterior checks. Every time the program returns the relaxation superoperator, it quietly checks whether Redfield theory is applicable. And if it's not applicable, it prints an error message.
Thank you. So one more question. How do you relate spectral density to phonon? You partially answered. In solid, are all the approximation derived for Redfield still valid?
Not exactly. It rather strongly depends on the phonon dynamics. You see, a phonon bus is quantum mechanical. You are coupled to an ensemble of oscillators in roughly the following way. Imagine you have a passing phonon through the system. It will move an atom. As soon as the atom is moved, some bond is stretched. As soon as some bond is stretched, some dipolar coupling has changed, and some shielding tensor has tilted a little bit. So a passing phonon jitters your spin Hamiltonian. And you can then translate, so it's a coupling between the spin operator and the displacement. Now, displacement you can express in terms of creation and annihilation operators in the lattice. And so now you have a spin Hamiltonian coupled to creation and annihilation in a second quantized lattice. And then frequencies have to match, but assumptions you can make about the phonons. In some cases, like Debye crystal, you can assume it's a bunch of classical oscillators. And then the J of omega is basically just the frequency spectrum of your phonon bath, weighted by the populations of each phonon mode. But then you see some phonon modes can be rather well isolated themselves, and if you couple spin system to them, you will start depleting the phonons in that mode. It's called a bottleneck. And then quantum mechanical effects kick in. So strictly speaking, Redfield theory assumes a purely classical bus. If you can make that assumption about your phonon bus, good for you. If the phonon bus is not classical, all hell breaks loose. You have to couple to another quantum system, which is then itself coupled to some, so it gets seriously complicated from that point onwards. As I mentioned, solid state relaxation theory is qualitative, right? The best shot was probably by Orbach, who has connected it in the way that I've just described. And there's a bunch of papers published very recently on really ab initio modeling this with DFT calculations of phonon spectral power densities. Nobody could ever get it right to better than an order of magnitude.
Okay, we have another. Lucio said, great talk. And he asked, do you have a similarly simple, elegant harmonic oscillator model to explain why spin relaxed to a temperature rather than to zero?
No. This model, if you go carefully through it, it relaxes your oscillator to zero. The weight on the spring eventually stops. If you put gravity into that system, you will start having an equilibrium state. So your spring is slightly stretched in the equilibrium in the presence of gravity. But Malcolm is here, and probably also Christian Banks, who just published a paper on exactly this. It is a really complicated matter, right? If you treat your bus quantum mechanically, and then quantum mechanically couple to that bus, but make an assumption that your bus stays in thermal equilibrium because it itself is coupled to something else, you then in your algebra, you get something called partial trace over that bus. And once you work through the mathematics, you in only a certain secular approximation, you get your relaxation superoperator to be Lindbladian, and then your forward and backward rate are correctly balanced, and you're actually relaxing to the correct thermal equilibrium. There are at least 5 different ways of hacking this problem. There's the famous non-uniform master equation, which mostly gets it wrong, except at very high temperature. There's a paper by Debary and Levitt, which proposes a method which is mostly working for just about everything, unless you're really at a millikelvin temperature. And then if you're on a millikelvin temperature, then God help you. That is, I think, my conclusion about this.
Thank you. So Khalif asked, what are the prominent mechanisms for spin relaxation at low or ultra low temperature?
spin phonon coupling. That's basically the only one there is.
Okay. Another question. Okay, that was it. Okay, we have does Redfield theory distinguish the relaxation of Zeeman reservoir from dipolar reservoir?
Could you say that again? Didn't catch everything.
Sorry. Does Redfield theory distinguish the relaxation of Zeeman reservoir from dipolar reservoir?
Right. So we're talking here probably about solids, right? The notion of dipolar reservoir is you have a solid, and then each individual spin would have a network of couplings, and those are coherent couplings, right? They are from H0. Magnetization will slowly diffuse through this network of the dipolar interactions. And this diffusion, although it is purely deterministic, right? If you run times backwards, it will refocus. Practically speaking, it's irreversible. There's nothing you can do on a spectrometer to reverse it, except in special circumstances. So this is the case where the magnetization is being lost into the environment in a coherent way. Strictly speaking, this isn't relaxation. Relaxation is the process where if you run time backwards, it doesn't come back. So now the second part of what I kind of read into that question, CSA relaxation is usually through stochastic processes, usually generally irreversible. Yes, if you're in a liquid, if your bus is classical, if your CSA tumbles, dipole-dipole interaction will tumble with it. And yes, Redfield theory will be able to independently say which part of your relaxation rate is due to CSA and which part is due to dipolar and which part is due to quadrupolar, for example. Those tensors will also cross-correlate, so you will have some mixed relaxation terms. Typically, if you look at a 3-spin system and look at every anisotropy in there, you would have about a couple of hundred secular cross-relaxation pathways and more than 10. I think it's in a 3-spin system, it's 15 different cross-correlations. So it rapidly gets more complicated as it goes. But the current software packages wouldn't even blink. They would spit it all out and they would classify your relaxation mechanisms. And in Spinach, for example, if you have a dipole and a CSA, and you want to know how much of it is due to CSA, just put the dipole to 0 and take a look.
Perhaps the last question. It seems like tau C is omitted in numerator in equation for J omega 0.
Correct. Yeah, it's a typo.
Okay. We have several questions, but as Michael pointed out, we have several excellent spin dynamics lecture by Professor Kuprov available on YouTube. You can continue discussion in the breakout rooms.
Actually, yes. So the full gory detailed derivation of fully quantum mechanical Redfield theory is on YouTube. And it's a funny lecture. It's, I think, an hour and a half long, and it looks like I just stepped in front of the board and derived everything. Nothing could be further from the truth. That lecture is a montage of 5 different unsuccessful attempts where I made a mistake in 5 different places. And then I cut 5 different videos and put them into one video that looks smooth. But it's there, yeah.
Okay, so since we are running out of time, I would